Hello everyone. This is the third video in the series about me making a monolithic Cassegrain telescope, and in this video I'm going to show you the last part of the project. It all started about half a year ago with a visit to Richterhorst, who showed me how he made these very tiny telescopes by hand, and this visit inspired me to try and make one myself. In the two previous videos I discussed optical design and raw glass machining and polishing. And in this video I'm going to talk about the really hard part of this project, which is making two of the optical surfaces aspherical. And of course we're also going to take a look through the telescope itself. Now, even though I left a ton of details out, this video still became quite long. So maybe pour yourself a drink first in order to make it all the way to the end. The previous video ended with a Cassegrain configuration in which all the optical surfaces were either flat or spherical, which results in a large focal spot. And the only thing left to do now is to correct the shape of the primary and secondary mirrors R2 and R3 by only a few microns. Here at the primary mirror we need to remove around 7 microns in this radial profile, and at the secondary we need to remove a maximum of 4.5 microns with this particular profile. A few microns does not sound like much, but this very small correction makes a huge difference in the optical performance. Unfortunately, it's not just about removing a few microns here and there. In the previous video I also mentioned that the margin of error in the conical surface shape needs to be smaller than, let's say, 40 nanometers. But I did not tell you why that is. So let's first have a look at how I got to this value. The precision required is basically due to the wavelength of visible light, which by itself is in the order of half a micron. Here's our telescope configuration again, and depicted are rays originating from a point source at infinity and ending up in a single focal point. And I've used rays to describe how light refracts and reflects in the telescope. But light is not rays, it's waves, so the ray lines merely indicate the direction of wave propagation. Because of the wave character of the light, it's not just important that all the paths lead up to a single point. They should preferably also cover the same length in wavelengths. In effect, what we want to achieve is that light entering the telescope in phase on one side should arrive at the focal plane also in phase. And this requirement is necessary to achieve the maximum resolution for the optic, the so-called diffraction limit. If the light arrives out of phase in the focal plane, the energy will be distributed into a larger area, resulting in a degradation of the maximum resolution. In these images, the effect is illustrated for a spherical aberration. In principle though, every surface flaw in an optical system can cause deformation of the wavefront and lower the maximum achievable resolution. We can calculate the wavefront error in the currently uncorrected device with optical design software. And if we do that, we will find that the wavefront error introduced by the optic looks something like this. The area of the graph represents the surface of the entrance pupil, and the z direction of the graph shows the total phase change introduced in the wavefront. Now you see that the differences are approximately 23 wavelengths at 550 nanometers, which is very large. And to get rid of the error, we have to slightly modify the shape of some of the optical surfaces by several microns. But at what point is the performance of an optic no longer limited by the wavefront error? One of the simplest criteria used is that the total peak to valley error in the wavefront should be smaller than a quarter of a wavelength. And this is actually kind of a coarse simplification, but for convenience, let's stick with it for now. The total wavefront error is the sum of all the errors introduced by the 4 individual optical surfaces, so for each individual surface the tolerances are quite a bit tighter. If we look at our current design, there are two types of surfaces. Refractive ones, where light crosses an interface between air and glass, and reflective surfaces. Now, there's a distinct difference between wavefront errors introduced by these two types of surfaces. Roughly speaking, we can state the following. For refractive interfaces between air and glass, the wavefront error is approximately half the surface shape error. And the way that we can intuitively understand this is that the effect of refraction is proportional to the relative difference in the refractive indices between the two media, which is in this case 0.5. But for a reflective surface, the wavefront error introduced is actually larger than the surface error. And we can understand this if you consider that any difference in distance between ideal and actual surface is covered twice by the light in reflection. So for reflection, the wavefront error is approximately 2 times the surface error. Now, as I just told you, these are very crude approximations. In practice, the error introduced is also influenced by many other factors, and I'll place a link in the description to a website where very detailed information on the effects of aberrations can be found. The bottom line is that reflective surfaces are about 4 times more sensitive to errors in surface shape than refractive ones. But what does this mean for the manufacturing accuracy of the reflectors that we now need to modify? Well, let's assume for a moment that the contribution of the refractive surfaces can be ignored and that the error is only due to the 2 reflectors. This means that the error allowed per surface is a quarter lambda divided by the square root of 2. And this is due to statistics by which some of the errors level out. But since the wavefront error is 2 times the surface error, this means that the surface error cannot be bigger than lambda divided by 8 times the square root of 2. So what is the wavelength lambda in this case? Well, unfortunately for this particular configuration, the light is inside the glass when it reflects, and the wavelength inside glass is not equal to the wavelength in vacuum or air, but this wavelength divided by the refractive index of glass. And this means that the wavelength in the glass is considerably smaller. And altogether this results in a maximum surface error value of 32 nanometers, which is even smaller than the value of 40 nanometers I just mentioned. For reference, 32 nanometers is about the length that your hair grows in about 5 seconds. Before you can actually make something with such a high accuracy, you first need to be able to measure with preferably a better accuracy. And one of the methods available is an optical method known as interferometry. The principle of this method is that we measure the shape of a wavefront by making it interfere with a wavefront of well-known shape. Now, if both wavefronts used for the test are either monochromatic or coherent, interference between the 2 wavefronts is observed. Basically, the small spatial variations between the 2 wavefronts create a fringe pattern consisting of dark and bright lines, which indicate where light is either in or out of phase. And this pattern contains very detailed information about the difference in shape and position between the 2 wavefronts. There are many different types of interferometry. For nearly flat or spherical surfaces, we can use a proximity method. Here the surface under measurement is brought very close to a reference surface, and when illuminating the gap with monochromatic light, an interference pattern can be observed in the combined reflections of the 2 surfaces. For example, here you see how that looks if I bring the flat front surface of the telescope in close contact to a flat reference surface. We observe these fairly straight and equally spaced interference lines, which is exactly the pattern that one would expect from 2 flat surfaces. And any curvatures in the fringes can be related to differences in shape between the 2 interfaces. Unfortunately, we cannot use the contact method to measure the aspherical interfaces in the current telescope, because it would result in too many strongly curved fringes, which are very hard to interpret. So we have to use special hardware and software to do this. One of the aspherical surfaces we need to modify is concave, so in principle its shape can be measured very similarly to any standard concave telescope mirror. The only issue here is that compared to, let's say, a normal size mirror, this one has a very small diameter of about 18 millimeters and a radius of curvature of around 42 millimeters. And this means that we need an interferometer that can handle a mirror this small and curved. Now, I decided on building a simple confocal Michelson interferometer, and schematically the setup looks like this. A diode laser is pointing through a gradient index lens to create a strongly divergent beam of coherent light, and this divergent beam is then split into 2 separate beams. One beam continues towards the mirror under measurement, and the other goes into the spherical reference mirror, which creates a spherical wavefront. Now the two reflected wavefronts return through the same beam splitter and are then recombined on this side where they interfere. And the resulting interference pattern can be recorded with a camera and evaluated using software. Here you see the actual setup that I built. In the center, the beam splitter, with to the right the laser and the gradient index lens. Here is a telescope with the surface of the secondary facing the beam splitter. The telescope itself is placed on an XYZ stage to be able to accurately manipulate the position of the reflected wavefront with respect to the reference wavefront. And this here is the spherical reference mirror that I made from a piece of clear ceramic. And here's the camera and some lenses to project the fringe pattern on the CCD. The interference pattern is recorded with a PC and converted to a wavefront plot using a shareware program called DFTfringe. This is a very nice open source program. I'll place links in the video description to more information and a download location. In this software you can set the parameters of the mirror under test, like diameter, radius of curvature, desired conic constant. The next step is that you import the interferogram and assign which area you want to include in the measurement or which one you want to exclude. And next you can do some low frequency spatial filtering on the interferogram, for example, to filter out intensity gradients or ghost fringes. And in a few mouse clicks the software calculates very accurately the shape of the wavefront. By the way, this hole in the interferogram is not something physical. It's because of an area that I excluded in the interferogram because it contains a nasty reflection originating from the beam splitter. In order for the software to work correctly, the interferogram needs to meet specific criteria like good contrast and clear, smooth and well separated fringes. Can't really go into all the details here. Instead, I'll link to a few videos by the developer of the software himself. So this setup allows for doing very detailed measurements on the shape of the secondary mirror with nanometer scale precision. Since the amount of material that needs to be removed is just a few microns thick, we're going to use pitch polishing as a method to achieve this. And in between polishing actions, we're going to use interferometry to check for the effects on surface shape. And pitch polishing is actually almost an art, and it requires detailed knowledge of how the polishing process works and how optical pitch behaves, which is a bit beyond the scope of this video. So I'm just going to briefly touch the surface. Here's a schematic of a glass interface being polished using pitch and a suspension of cerium oxide particles as the abrasive. The cerium oxide particles generally have a size between a few microns to slightly submicron, and they get partly embedded into the soft pitch surface. They scrape along the glass interface and while doing so remove small amounts of material. The cerium oxide is actually not sharp and hard like the silicon carbide grains used for grinding, but it's generally about the same hardness as the glass itself. This makes that the polishing process is a very mild but also a very slow process. And in order for it to work correctly, it requires very good and intimate contact between the tool and glass surface at all times. Now, for making a spherical surface, you want the polishing action to be as uniform as possible over the surface. But for making an A-sphere, you need to remove more material in specific locations. In order to achieve that, you could use very local deterministic polishing, for example by moving a Dremel over the surface with the right contact time distribution. But if you do not control all the parameters here exactly, it's a bit like digging with an excavator. You can very quickly remove too much material and at the same time create a high surface roughness. Now, with a little more money, you could of course buy a dedicated CNC polisher. But for this project, I wanted to try a different approach, which involves the modification of the active polishing area of the pitch tool. And to explain how this would work, I need to tell you a bit about the important parameters in the polishing process. So during polishing, we gradually remove an amount of material. But how much exactly? One of the important parameters is the total contact time during polishing. The longer we polish, the more material we remove. Next, there is the speed at which the two surfaces move along each other. And intuitively speaking, both time and speed will have a linear relationship with the amount of material being removed. Other parameters that play a role are the pressure applied and the roughness or the effectiveness of the abrasive. So the harder we press, the more material is removed in the same amount of time, and something similar can be said about the roughness of the abrasive. But empirically you can establish that the relationship between removal rate and pressure or abrasive grain size is generally not a linear one. So what we can do is bring these two parameters together in a coefficient C, and as long as we keep the pressure and the abrasive constant, C will also have a constant value. So we arrive at this equation that summarizes the parameters in the polishing process and is sometimes referred to as Preston's law. And what we can do now is use this relationship to create a tool with a contact surface shape that will generate the desired aspheric profile. For example, for the primary mirror we need to remove this specific radial profile. Now, assuming that we would use rotation around the central axis of the object, we could transfer this particular removal profile onto the tool directly. So basically you create contact areas that copy this profile. Now you might argue that this shape is probably incorrect because velocity on the outside of the tool is much higher than on the inside. But contact time has exactly the opposite relation with radius. So these two effects actually level each other out, which means that we can almost directly transfer the desired profile into the contact area of the tool. Almost, because there's this slight effect of curvature on the contact time. The reason that we need to use pitch is that in order for this to work, the two surfaces need to be in very close contact all the time. And with material being removed constantly, we need something that can deform during the polishing process and set itself to the changes in the glass shape. Optical pitch is actually a very high viscosity Newtonian liquid, and it will deform irreversibly when a force acts upon it. The viscosity of pitch itself is strongly dependent on the temperature, which is not ideal given that polishing is based on friction and generates quite a lot of heat. And this is one of the downsides of using pitch, because it can change shape very fast and give very unexpected results if you don't control the temperature. To make tools with a particular surface shape, I first made molds with the help of a 3D printer. I used a printer that is normally used for dental fabrication or jewelry, so it's very accurate. And the printer was sent to me by 3BFab, a Turkish manufacturer of 3D printers. It was actually supplied to me for other projects, but since I had it here and it works very well, I figured why not use it for this project as well. Making the molds was actually pretty easy. I just made STL files using CAD software and printed these in dental resin. The molds contain indentations that mimic the removal profile, and so by pressing a warm and still moldable pitch tool against the mold, we can create tools with the inverse shape. And this gave me a very flexible way to make various tools with specific surface profiles. Now the big question is, can we make accurate aspherics using this concept? To find out, I started polishing the secondary mirror with the appropriate tool shape. And in a global sense, indeed, you can remove material in the right profile with this method. For example, after some time polishing the secondary, this is the general change in shape. And indeed, it seems to match with the profile that I intended to remove here. But if we compare it directly with the exact shape of the specific conical surface and look at the deviations from the target shape, these deviations are actually quite large. We observe zones where the surface is either too low or too high, and in fact these deviations are far from the target accuracy of 32 nanometers. If you look at the color scale, the height deviation is at least 2 waves, suggesting a surface error of about 500 nanometers. I found that the main reason for these deviations is that the contact area shape in the tool cannot be made with sufficient accuracy for tools this very small with the method involving molds. So the replication process from mold into pitch contact surface is not very accurate. But even if you could get the initial contact shape exactly right, another problem comes up during polishing. The contact area is also slightly changing during the polishing process because of the viscous properties of pitch. And this means that in some radii you will remove too much material and in others too little. And on the submicron scale, this results in these radial deviations from the target shape, which are generally in the order of a few hundred nanometers high. I tried a lot of things, for example, making separate tools to remove material in a specific zone. But in fact, most corrective tools just made things worse. Eventually, after a lot of trial and error, I got a little better at designing tools intended for the removal of material in a specific part of the surface. And here you see the final surface profile that I kept for the secondary mirror. In principle, all these profiles were taken under different angles on the surface and should very well be between the two indicated boundaries and be very smooth. But as you can see, that's not the case at all. So you might wonder, what about the center and the very edge of the surface? Well, these actually do not pose a real problem. If you look at where light reflects on the mirror surface, it's only in a region a few millimeters wide, and the rest of the surface is basically irrelevant for the performance of this mirror. Anyway, this mirror is not really within spec, but instead of spending another few days on a very frustrating activity, I decided to stop here and move on to the next step, which is figuring the primary mirror. Measuring the convex primary mirror cannot be done with the same setup as I used for the secondary, and I had to come up with a different strategy for correcting this surface. What I did was measure the wavefront exiting the full telescope while doing the corrections on this surface. And in principle, this is possible because we have the other three surfaces in, well, approximately the right shape. Now, by steering on the quality of the telescope output directly, we can make the corrections using the performance of the total system rather than just making the surface to a certain design specification. So, how can this be done? What we want to achieve is that the light on this side of the telescope is focused into a single point, which requires a spherical wavefront. But right now, the current spot is, when projected, still incredibly big and messy and very far from what we want. So the goal here is to simply make the wavefront exiting the device spherical, which at the same time will remove this aberration. But of course, we need a way to measure the wavefront shape during this process. The solution I came up with for doing this is the point diffraction interferometer. And this interferometer consists of nothing more than a glass plate with a semi-transparent layer that has a fairly low transmission of, let's say, 0.5%. And the plate also contains a tiny pinhole. Here, by the way, is the point diffraction interferometer plate, this plate that I used for the experiments, which can be bought from Astro Electronic. So, if we bring this plate into the beam near the focal point, the wavefront is partially transmitted, be it strongly attenuated in intensity, except for a small portion of the light that is passing the pinhole. Because the pinhole is so small, it diffracts this light into a spherical wavefront. And now suddenly we have a spherical reference wavefront available for testing. Now, in order for this to work properly, we need to match the total light through the filter and through the pinhole. And that is the reason why most point diffraction interferometer plates contain multiple and differently sized pinholes, so you can choose the most appropriate one and achieve the best contrast. Now, if you think that this method just sounds too good to be true, in fact you are correct. Point diffraction interferometry really sucks when you want to make a clear interferogram. It can generally only handle a very limited number of fringes with good contrast, and it's hard to get the balance right between the amount of light passing the pinhole and the light passing the filter. It is, however, possible to examine the fringes visually. So what we can do now is just start polishing with the appropriate surface profile tool and try to get the fringe count down in the interferogram, ideally to only a few fringes. And then once we have a very limited number of fringes left, we try to make additional corrections and to get as close to the interference pattern of two spherical wavefronts as possible. Here you see the interferogram at the start of the figuring process, which looks a lot like you would expect. And the interferogram is so bad that we cannot even observe all the fringes on the outside. And the focal spot is so big that it actually illuminates neighboring pinholes. In this case, you could certainly not create an accurate wavefront map from this using DFTfringe. But when you start polishing with a tool, you indeed also gradually reduce the number of fringes, which indicates your wavefront is getting flatter. Now, at some point you can try to unwrap the fringes to create interferograms that you can sort of interpret, And because of the bad image quality, I had to do the interpretation of the interferograms in my head, which was not always a good idea because it led to a couple of very silly correction mistakes. Again, in the end, I did not get where ideally I had planned to be, so no perfectly straight interference lines here. But I found out that to improve things further, I basically had to start all over again, and I simply did not have time for that. So I ended up with a device that has a wavefront accuracy of about 1 plus lambda instead of the intended smaller than a quarter lambda. And on top of that, it has radial zones and a general surface roughness that is way too high. Even so, let's just take a look through it anyway. So first I want to show you what happened to the size of the focal spot. And here you see the focal spot compared to what it was before the correction of the primary mirror. It's quite a difference, right? It's not perfect, but it's really so much smaller. So just steering on minimizing the wavefront error actually worked for removing the spherical aberration. Anyway, given this focal spot, it should also definitely give us a much better image than the uncorrected scope. To find out, we first have to coat the two surfaces with something reflective, like a thin layer of silver. And for this I used my PVD setup, which was discussed in another video. I evaporated a thin layer of silver on both surfaces in a vacuum chamber. By the way, any thickness variations in the reflective layer are irrelevant because we're coating from the outside, so it's the glass surface that's defining the actual mirror surface. So after coating both surfaces, I added a layer of black spray paint while using some tape to mask entrance and exit, and here it is, the monolithic cassegrain. So let's take a look through it and see how it performs. If you've seen the previous video, you might remember the view of the two exhaust pipes on the nearby roof. And the huge spherical aberration made them look pretty fuzzy and unsharp. And this is what they look like now in comparison. Again, not a perfect image, but even the lichens on the roof show quite a lot of details if you zoom in. Still, there is this general fuzziness in the image, and it would be good to know if this can be attributed to the surface error of 1 lambda. I mean, after all, this is a view through a double glass window. My first plan was to take a look at some details of the moon, but it turned out that the moon could not easily be observed during the days that I was working on this video. So instead I settled for a view to an apartment building 400 meters from my home. I agree, it looks a bit intrusive, but important optical experiments always prevail over a bit of privacy. So here is a balcony with some stuff on it, and because of the magnification of the telescope, we can observe a lot of small details that are impossible to see with the naked eye. Let's do a quick comparison of the tiny telescope with a 300mm telelens. And in order to make this a fair comparison, I had to limit the aperture of the 300mm lens to that of the monolithic telescope. Now, there are two things that really stick out in the images. The magnification of the monolithic telescope is quite a bit larger, and it turns out that the effective focal length is 450mm, which is quite a bit off from the focal length that I intended to make. So apparently all my tweaking around with the primary and secondary changed the focal distance quite a bit, and this is definitely something I should look into. And the other thing is a general loss of contrast, and I think this is mainly due to the fact that the black paint to reduce stray light is not very effective, which means that both the walls of the scope as well as the baffle still scatter quite a lot of light instead of absorbing it all. And this will lead to a significantly lower contrast for sure. Now, if you look at the details of the images, you can also observe some fuzziness, like for example on these bolts holding the balcony constructions together. And since both images have the same aperture, this fuzziness can only be attributed to the bad wavefront quality of the tiny telescope. But I have to admit, the general image quality is not as bad as I expected it to be, based on the earlier wavefront measurements. So there's definitely still a lot of room for improvement, especially in contrast and sharpness, but I will leave that for some other time. Anyway, hope you found this interesting. Cheers! taking an afternoon nap, are we? Anyway, I've got great news. Just got a call from Jack at sales. He's sold 200 of these. 200! The only thing is, they have to be ready at the end of this month. So, guess no more naps for you, eh?